Today we continue our series on early astronomers, the birth of science, and the origins of calculus. Last time we talked about the two models of the universe, the heliocentric model and the geocentric model. As far as we know, Aristarchus was the first to propose a heliocentric model, but he attracted virtually no following. The vast majority of ancient Greek authors favored the geocentric model. I mention here some of the most notable ones. Anaximander was the first to clearly articulate it. Aristotle was not an astronomer, but that did not stop him from weighing in. Hipparchus has been called the father of trigonometry and the greatest astronomer of the ancient world, but he was not the most famous. That title goes to Ptolemy, who borrowed heavily from Hipparchus in writing his masterpiece, the Almagest. Although Ptolemy gives much credit to Hipparchus in the Almagest, Hipparchus's own writings were lost to history. In fact, the Almagest was the only complete and comprehensive treatise on astronomy to survive from the ancient world. Thus, it is Ptolemy who is most remembered. Furthermore, Ptolemy was the last to make any refinements to the geocentric model, and so it became known throughout the rest of history as the Ptolemaic model. No one seriously questioned it until Copernicus came along some 1,300 years later. I want to explore with you how the Ptolemaic model works, with occasional comparison to the heliocentric model. In the end, you will understand the elegance and nuance of the Ptolemaic model better than anyone you will ever meet outside of this class. I hope this discussion illustrates how two different scientific theories might compete with each other to explain the same set of observations. As another example, Newton's theory of gravity seemed to work just fine for hundreds of years. Then Einstein came along with a new theory of gravity. However, it was not immediately clear which one was better. Einstein's theory was proven to be superior only later, when new and very cleverly conceived observations were recorded. I also hope that this discussion will give you a better understanding of what's going on in the night sky, so that you can better appreciate and enjoy making your own observations whenever you get the chance. Finally, as to why the ancient Greeks pursued the study of astronomy so assiduously, keep in mind that they were seafarers. Their economy was based primarily on olive oil, wine, and maritime trade. In contrast to the situation of the Egyptians and the Babylonians, navigation by the stars was essential to the Greeks' prosperity. The descriptions that follow, unless otherwise stated, represent the movements of the heavens as Ptolemy would understand them. Last time we introduced the concept of celestial spheres. The outermost sphere contains the fixed stars. They are called fixed because they remain in the same place relative to each other as the sphere revolves around the Earth. There are also separate spheres for the sun, the moon, and the planets, with a few extra thrown in for philosophical or religious reasons. This is an illustration of the Ptolemaic model from 1542. The Earth is at the center, and it does not move or rotate. Then comes air and fire, followed by the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and the fixed stars. And then there are the heavens beyond. The planets beyond Saturn were not known. The stars, the planets, the sun, and the moon each needed their own spheres because these bodies and the spheres that contained them all revolved around the Earth at different rates. In order to understand the discussion that follows, we need to agree on the orientation of the diagrams that we will be looking at. Imagine yourself in outer space, looking down on Earth from above the North Pole. For simplicity, imagine that we here in Northern California live on the equator, and let's ignore the tilt of the Earth's axis. Here we see the Washington Monument and the Transamerica Building. Of course, they are not to scale. I'm showing them here as reference points. Now, if we imagine someone standing in Nebraska, anything to the west of the person will be to our right on this diagram, and anything to the east will be to our left. If that person in Nebraska watches a full moon throughout the night, they will see it rise in the east and set in the west, just as all celestial bodies do. From our vantage point, the moon is revolving clockwise around the earth. All celestial bodies, stars, planets, sun, and moon, rise in the east and set in the west. And so, from our vantage point in space above the North Pole, they all revolve clockwise. This is a modern illustration representing the Ptolemaic model. Notice that the planets, as they revolve around the Earth, also execute occasional loops called epicycles. We will come back to these later. But there is something else going on that is curious. This illustration, like all that I have seen, shows that all the spheres, except that of the fixed stars, are rotating counterclockwise. We are still looking down from above the North Pole, so what's going on? To answer this question, let us first consider just the sun and the stars. Imagine this person standing here at midnight. The sun is long gone, but the person knows that the sun is directly beneath their feet by the very fact that it is midnight. The constellation Gemini is directly overhead. Gemini is one of the constellations of the zodiac. The other 11 are shown here, forming a great circle around the Earth. They are separated evenly by regular intervals of 30 degrees. The following midnight, everything looks pretty much the same. However, this person understands that in order to detect subtle differences in the rotation rates of the different spheres, you have to look at the sky night after night for weeks or months. They also know that you have to note the positions of the heavenly bodies at the exact same time every night, so that your observations are not affected by their 24-hour cycles. In this case, after about 30 days, Cancer is now directly overhead at midnight, and Gemini is 30 degrees to the west. The sun has made exactly 30 trips around the Earth, of 360 degrees each. It turns out that Gemini and all the other constellations have traveled 361 degrees each day, for a total of 30 revolutions plus an extra 30 degrees. After 1 year, Gemini is directly overhead once again. The sun has made 365 trips around the Earth, and the stars have made 366 trips around the Earth. An important point to be noted here is that the sun is the source of two key units of time. One 360-degree revolution, for example, equals 1 day, while 365 trips from, for example, one summer solstice to the next summer solstice equals 1 year. So the sun is ultimately the benchmark against which we measure the rates of revolution of the other spheres. However, there is a problem. The sun, of course, is not visible at night, and so we can only measure the motions of the planets against the backdrop of the stars. It turns out that the moon, along with Mars, Jupiter, and Saturn, revolve around the Earth more slowly than both the sun and the stars, so that, relative to the fixed stars, they revolve counterclockwise. That's why the illustrations of the Ptolemaic model show the planets and the moon rotating counterclockwise, or west to east. The ancients were switching reference frames and taking the sphere of the stars to be motionless. Even the sun is shown to be revolving counterclockwise in the Ptolemaic model, 1 degree per day, relative to the fixed stars. So now we can understand why illustrations show the spheres of the moon, sun, and planets revolving counterclockwise. It is simply a matter of convenience so that the ancients could use the fixed stars as reference points. By way of comparison, the heliocentric model makes it quite easy to illustrate what's going on. The fixed stars, for all practical purposes, truly are fixed, as is the sun. As the Earth revolves around the sun at a rate of 30 degrees each month, an observer who saw Gemini directly overhead at midnight 1 month ago will now see Cancer directly overhead at midnight, just as this diagram shows. Remember the phases of the moon. This diagram actually works just fine with either model because in both models the moon orbits the Earth once a month. Using either model, we can predict that if we see a full moon at midnight, one week later we will see a half moon rising in the east at midnight. Here's another way of demonstrating the same idea. If you look at the moon night after night at the same time each night, as illustrated here, you will note that it is roughly 12 degrees closer to the east every 24 hours. Ptolemy would say that it is moving slower than the sun and falls behind the sun by 12 degrees every day. So far, it has been relatively easy to accept the geocentric model as working just fine. Things only get tricky when we try to account for the motions of the planets. It is unusual to be able to see all 5 planets at once, but this photograph managed to capture all of them just after sunset. Soon each planet in turn will set in the west. However, if you looked at the planets at the same time each night, night after night, you would notice a very different sort of change in position. Most of the time, each would be relocated a bit to the east each successive night. Ptolemy imagines them revolving more slowly than the sun, just as the moon does, with each one generally drifting east at its own rate. So far, so good. But here's the tricky part. Periodically, each planet in turn will stop losing ground to the sun and instead will gain ground on the sun, so that if you plot its position night after night at the same time each night, it will now appear to be shifting towards the west. This shift is called retrograde motion. The duration of retrograde motion and the interval between periods of retrograde motion is highly predictable for each planet, but varies substantially from one planet to another. For example, retrograde motion for Mars lasts for weeks, while for Saturn it lasts for months. In order to account for these periods of retrograde motion, Ptolemy's model postulates that each planet enters a loop called an epicycle periodically throughout its normal orbit. This animation will show the orbital paths for Mars and Jupiter, including their epicycles, according to Ptolemy. The circles associated with each planet are purely hypothetical and are designed to suggest a mechanism guiding each planet through its complicated motion. The larger circle associated with each planet remains stationary and represents the general orbital path, whereas the smaller circle, to which the planet is attached, rotates around its center while its center travels around the larger circle. The Sun does not have a smaller rotating circle because it does not need one, and it does not need one because it never changes its direction relative to the fixed stars. When I set the animation in motion in a moment, note the following. Whenever Mars and Jupiter are traveling on the half of their small circles farthest from Earth, they would appear to be slowly drifting west to east, night after night, to an observer on Earth. I say slowly because if the rate of movement in the animation was set to match planetary movements in the real world, the movements that you would see in the animation would be too slow to perceive. In contrast, during the time that the two planets are in the half of their small circles closest to Earth, they will appear to go into retrograde motion. This computer-generated illustration demonstrates the wide variety of patterns of epicycles necessary in order to make the Ptolemaic model work. So how do we understand the apparent retrograde motion of the planets within the framework of the heliocentric model? This animated video will simulate the path of Mars as seen from Earth, including its retrograde motion. Think of this video as time-lapse photography, showing the relative positions of Earth and Mars at the exact same time each night, night after night, over several months. The blue planet is Earth and the red planet is Mars. The pink cone traces the path of Mars, as seen from Earth, against the background stars. The retrograde motion will occur after Mars enters the rectangle on the left. The rectangle on the right will show a simultaneous view of Mars from Earth. Recall that the Earth revolves around the Sun at a faster angular velocity compared to Mars. Therefore, you will see Earth catching up with and passing Mars. If you observe carefully, you will notice that the apparent retrograde motion occurs just as Earth is catching up to and passing Mars. Thus, the apparent retrograde motion is due to the reversal of the positioning of Earth and Mars relative to the fixed stars as Earth travels past Mars, and reflects a more general principle known as the parallax effect. It's time to say a few final words about Ptolemy. When later scholars studied the Almagest carefully, they noted that wherever Ptolemy tried to add to what Hipparchus had already discovered, his results contained numerous errors. Some later scholars even suspected that he invented or altered much of his data to fit his theories. Isaac Newton called him the most successful fraud in the history of science. So was Ptolemy a brilliant astronomer or a cheater? Well, maybe he was a little of both. We must remember that scientists are human. They have egos. Sometimes they commit fraud intentionally, but perhaps more often they fall in love with the theory so much that they either ignore or alter data that doesn't fit with their theory. The problem of scientific fraud is an old one and does not appear to be going away. Here are some headlines from earlier this year. Stanford president resigns after fallout from falsified data in his research. The research scandal at Stanford is more common than you think. This obviously raises a big concern. When should we accept a scientific claim or theory as valid, and when should we be skeptical? Let's keep that question in the backs of our minds as we continue this series on the history of science. After we finish with the scientific revolution, we will be in a good position to try to answer that question, which in turn will bring us to a general discussion of the philosophy of science. So now we come to Copernicus. As a young man, Copernicus studied liberal arts, medicine, church law, mathematics, and astronomy, both in Poland and in Italy, and quickly developed a reputation as a brilliant scholar. Of particular importance, he learned that there were some problems with the geocentric model. For one thing, two very different versions of the geocentric model had been proposed, and there was controversy over which one was correct. In one version of the model, the planets Venus and Mercury are said to lie between the Moon and the Sun. In the other version, these two planets are said to lie beyond the Sun, farther away from Earth. Obviously, at least one version must be false, and if observations could not prove one false and the other true, maybe they were both wrong. So, when Copernicus developed his heliocentric model, he found two things that were immediately and immensely satisfying. First, simplicity. There was no need for complicated epicycles that defied any coherent explanation. Secondly, a pattern emerged. The period of a planet's orbit correlated with its distance from the Sun. The farther a planet was from the Sun, the longer was the period of its orbit. This correlation suggests the possibility that one could find a general formula relating the two. As it happens, symbolic algebra had recently come into use in Western Europe, somewhat before the time of Copernicus. It's not clear whether Copernicus tried to find such a formula, but the possibility certainly tantalized some of those who came after him. In modern notation, the equation might have this general form. Let r equal the distance from the Sun of a planet. Let p equal the orbital period. Then p equals a function of r. This was something new, and this was the genius of Copernicus. Aristotle believed that the subject of mathematics was inferior to philosophy and logic. His view was that mathematics was merely a tool and had no role in understanding the true nature of things and their causes. In contrast, Copernicus believed that nature was essentially mathematical in its structure, and that only the power of mathematics could reveal the true nature of the planetary system. We haven't come to Kepler yet, but we will. Spoiler alert, here is Kepler's third law. P squared equals k times r cubed, where k is a constant. In fairness to Ptolemy, his orbital paths with their epicycles are representative of a particular family of geometric figures known as epitrochoids. Furthermore, thanks to Descartes and the analytic geometry that he invented almost 200 years after Copernicus, we now know of the equations that describe epitrochoids. And here they are. They are fairly complicated parametric equations. There are two dependent variables, x and y, one independent variable, t, which presumably would stand for time, and three parameters, a, b, and h, as illustrated here. Presumably, each parameter might need to be different for each planet, with no fundamental principle to explain the varying values of these parameters. By way of comparison, Kepler's third law is much simpler. There is the dependent variable p, the constant k, which is the same for every orbit, and one independent variable r, which is a well-defined quantity that a scientist could potentially try to measure. Most importantly, there is no need to interject additional parameters of no known origin. In the philosophy of science, a razor is a general guideline or rule of thumb. One example is known as Occam's razor. In comparing two different explanations for the same phenomenon, the one that requires fewer unjustified or improbable assumptions is probably the correct one. Einstein said something very similar, which can be paraphrased as, "Make things as simple as possible, but no simpler." We can already see that the heliocentric model is the simpler one, and most likely the correct one in accordance with the razors of Occam and Einstein. However, Copernicus was not able to prove it. We will get to that next time.